So it's with great pleasure that I welcome Professor Murry Salby, who has diverted a trip from America to give this lecture and to have a meeting actually on Wednesday. So it's been a great privilege to have him to stay. So I'm going to hand over to you now, Murry, because I think the sooner we get going, we'll be kick-off at 1:15. How much time there will be for Q&A will be dictated by the time, and I apologize if we simply have to say we have not got the time.
Thank you, Philip. Climate is a subject of limited understanding, in significant part because observations are inadequate. Yet it's a subject on which almost everyone has an opinion. Tonight's presentation concerns carbon in the atmosphere. Almost all of it is in the form of carbon dioxide. I will first review existing evidence of the human contribution to increase CO2. If you want the details, they're out there. I'll then present new evidence, which isolates the role of fossil fuel emission in the 20th century increase of carbon dioxide. I'll close with a retrospective that places the treatment of this subject into historical context. Before we turn to the main subject, I promise to show you why CO2 cannot be a pollutant. How many of you have seen an image like this? Right. It's a favorite of the media. This image has become the poster child of CO2 emission. There's just one complication. In the vernacular of Mark Twain, never let the truth get in the way of a good story. These are cooling towers. What's emerging from them isn't CO2, it's wawa, a cloud of microscopic droplets that have condensed from water vapor. It's no different than those fluffy white things up in the sky. Exhaust from combustion of fossil fuel emerges from the tower at the left, the combustion flue. But even that plume is not CO2. What is it? Close inspection provides a clue. Immediately above the flue, the emission plume is invisible. The visible part is likewise water. Droplets that condense after water vapor is cooled through mixing with surrounding air. From where did that water vapor come? It has the same origin as steam in car exhaust on a cold morning. Combustion is a form of oxidation. The same process powers the human body. In it, CO2 cannot be produced without simultaneously producing water vapor. CO2 and water vapor are the products of perfect combustion. They are produced even when there are no byproducts, no real pollutants. Their role is illustrated by simple fuel, methane. For every CO2 molecule produced, its combustion produces 2 molecules of water vapor. More complex fuel is illustrated by Appalachian coal. For every 3 CO2 molecules, Its combustion produces 2 molecules of water vapor. In regard to climate, whether the ratio of water vapor to CO2 is 2 to 1 or 2 to 3 really doesn't matter. Here's why. Plotted here is the atmosphere's opacity at wavelengths of infrared radiation, collected over all greenhouse gases. It's what traps radiant heat at the Earth's surface. It's also the premise for the EPA's finding of endangerment by CO2. Notice, over almost all wavelengths, the opacity is already 100%, the maximum possible. In green is the contribution from CO2. It represents less than 10% of the overall opacity. What provides the rest? Almost all of it comes from water vapor, including derived cloud, makes its contribution even greater. Notice, even at those wavelengths where CO2 absorbs radiation, water vapor absorbs over half of the maximum that's possible. Only what remains, less than half, is influenced by changes of CO2. In this plume, water vapor that's emitted with CO2 is produced through the same process that produces CO2. Its heat trapping capacity vastly exceeds the heat trapping capacity of CO2. CO2 will be a pollutant the day that water vapor is a pollutant. It follows that energy sources which circumvent CO2 emission are neither cleaner nor greener. They're just different. Now to this evening's main subject. What role does such fossil fuel emission of CO2 play in the increase of atmospheric CO2? The IPCC's position is simple. All of it. What is reality? A clue comes from changes of fossil fuel emission of CO2 and contemporaneous changes of atmospheric CO2. During the decade before the turn of the century, fossil fuel emission increased almost linearly. During the subsequent decade, it also increased linearly, but 3 times faster. The area under the curve represents the CO2 that was emitted into the atmosphere. Far more was emitted during the second decade than during the first decade. "200% more. During the same period, atmospheric CO2 also increased linearly. In the first decade, it increased by about 20 parts per million by volume, ppmv. During the second decade, its increase was virtually identical. Fossil fuel emission during the second decade was 3 times that during the first decade. Yet its impact on the increase of atmospheric CO2 was virtually zero. Where the additional anthropogenic CO2 ended up cannot be said. Where it did not end up is unambiguous. The premise of the IPCC that increased atmospheric CO2 results principally from fossil fuel emission is impossible. If fossil fuel emission represented as little as 10% of the increase in atmospheric CO2, the atmospheric increase during the second decade would have been 30% greater than during the first decade. It wasn't even close. The disconnect between fossil fuel emission of CO2 and atmospheric CO2 should hardly come as a surprise. This is an estimate of the CO2 budget by the IPCC itself. Of total emission, human emission accounts for only a couple of percent. The rest, over 95%, comes from natural emission. Even a minor change of natural emission would overshadow human emission. The resultant of all of these contributions is net emission. The net rate at which CO2 is introduced into the atmosphere. It must equal the instantaneous growth rate of atmospheric CO2. That property follows from the observed record. In green is net global emission of CO2 from all sources. It has an average of about 1.6 ppmv per year. But between years, it changes by as much as 100%. Local observations of emission, all we have, reveal strong sensitivity to surface properties, especially temperature. The same dependence is manifest in global emission of CO2. Perturbations in temperature, for example, associated with El Nino and volcanic eruptions, introduce perturbations in CO2 emission. They do so by modulating physical and chemical processes behind CO2 emission, but only the natural component of CO2 emission. Human emission is independent of temperature. The strong coherence between surface temperature and CO2 emission determines the thermally induced component of atmospheric CO2, much of the natural component. A change of temperature corresponds to a change of CO2 emission. That determines the annual increment of thermally induced CO2. Adding those increments over successive years yields the evolution of thermally induced CO2. It evolves like cumulative temperature, the integral of temperature. In green is the observed evolution of atmospheric CO2. It has an upward trend of 1.6 ppmv per year, the average of net emission. Shaded is the range of thermally induced CO2 that's possible in light of observational uncertainty. We're interested in the increase of CO2 from values in the 19th century, about 280 ppmv. The part from thermally induced CO2 lies somewhere in the shaded area. Its discrepancy from observed CO2 then isolates anthropogenic CO2. The smallest possible increase of thermally induced CO2 corresponds to the largest possible increase of anthropogenic CO2. It provides an upper bound on the anthropogenic increase of CO2. The anthropogenic fraction of increased CO2 must be smaller than 33%. As we saw, the increase of atmospheric CO2 follows from net emission. The rate of net emission equals the rate of global emission into the atmosphere minus the rate of global absorption from the atmosphere. Mathematically, the rate of change of CO2 mixing ratio, R, that's the time derivative on the left-hand side, equals the rate of global emission, E, minus the rate of global absorption, A. This equation describes conservation of atmospheric CO2. It's the global average of the three-dimensional continuity equation used in climate models. The conservation equation is a fundamental physical law which must be satisfied by CO2 in the atmosphere. If this law is not satisfied, you might as well turn out the lights and go home. To grasp its implications, it's instructive to consider a mechanical analog. A feature of the Australian coastline is the sea bath, a saltwater enclosure free of surf and shark. Australia has many species of shark, not all of which are in the sea. To limit bacterial growth, the sea bath is continuously ventilated with seawater. What goes in eventually goes out. That's what we just saw for the atmosphere in the budget of CO2. In the sea bath, water is added at the rate of volume inflow and removed at the rate of volume outflow. The water level follows from the resultant of these opposing influences. The volume growth rate equals the net rate at which volume is added. That equals the rate of volume inflow minus the rate of volume outflow. Mathematically, the rate of change of water volume that's the time derivative on the left-hand side, equals the volume inflow rate minus the volume outflow rate. This equation describes conservation of water. It's a fundamental physical law that governs water in the sea bath. Now, the rate of outflow is proportional to the bottom pressure, which forces water through the drain. It, in turn, is proportional to the height, h, of the water column overhead. The deeper the water, the greater the bottom pressure, and the faster the water leaves through the drain. The conservation law can therefore be rearranged into the following form. The rate of change of height, h, equals the rate of emission into the bath, E, minus the rate of absorption from the bath, A, where emission is proportional to the inflow rate and absorption is proportional to the water's height. Absorption can then be expressed as height times the absorption efficiency, alpha. Alpha is proportional to the area of the drain. The bigger the drain, the faster the water leaves. Alpha has dimensions of inverse time. 1 over alpha defines the absorption time. It reflects the residence time, the characteristic time that water spends in the bath before leaving through the drain. The significance of alpha is illustrated by eliminating inflow. The conservation law then reduces to the rate of change of height is proportional to the instantaneous height. The evolution that satisfies this conservation law is exponential decay at rate alpha. After one absorption time, height is decreased to 37% of its initial value. Suppose the bath begins empty. Absorption from the bath is then less than emission into the bath. The water's height must increase. So too then does absorption from the bath. Eventually, height will increase sufficiently for absorption to just equal emission. Height then becomes constant. It represents the limiting value, an upper bound on height. The height which achieves this limiting condition is the equilibrium height. Since the rate of change vanishes, the conservation law then reduces to a balance of terms on the right-hand side. Emission equals absorption, which in turn is proportional to height. Rearranging gives the equilibrium height. It's just the quotient of the opposing influences on water volume. Emission divided by the absorption efficiency, alpha. Suppose now the equilibrium state is perturbed by adding auxiliary emission. A perturbing source with emission E prime. Absorption from the bath is again less than emission into the bath. The height must increase. That increases absorption from the bath. Eventually, the perturbed absorption will increase sufficiently to again just equal the perturbed emission. The perturbed height then becomes constant, achieving a new equilibrium. The perturbation in height, H prime, is related to the perturbation in emission, E prime, through the same conservation law. It describes conservation of perturbation water, the additional water introduced by the perturbing source. The fractional increase of equilibrium height then equals the fractional increase of emission into the bath. If emission is increased by 5%, equilibrium height is increased by 5%. Notice, instantaneous height never exceeds the equilibrium height, which represents its limiting value. In equilibrium, the perturbation in emission equals the perturbation in absorption. It follows that the perturbation of height depends inversely on the absorption efficiency alpha. If absorption is twice as fast, the perturbation of height is only half as large. The faster the absorption, the smaller the perturbation of height. Suppose now the perturbation of emission is eliminated. The perturbing source is switched off. Absorption is then unbalanced. It exceeds emission. Height must then decrease. It does so until height is returned to the unperturbed equilibrium, whereupon absorption again equals emission. Under these conditions, the conservation law for the perturbation reduces to the rate of change of height is proportional to the instantaneous height. Hence, the perturbation of height decays exponentially at rate alpha, restoring height to the unperturbed equilibrium. After one absorption time, the perturbation has decreased to 37% of its initial value. Notice, the response to perturbation reveals what cannot be measured directly: the absorption time, how fast water is removed from the bath. Back to the atmosphere. CO2 obeys a conservation law of the same form. Like height in the sea bath, CO2 mixing ratio R is determined by competition between emission into the atmosphere, E, and absorption from the atmosphere, A. CO2 has an equilibrium mixing ratio equal to the quotient of global emission and absorption efficiency, alpha. Alpha is just the absorption, scaled by CO2 mixing ratio, R. We know R. We don't know global absorption, A. The IPCC thinks it does. A is 150 in gigatons of carbon per year. R is 750 in gigatons of carbon. The absorption efficiency is then 5 years to the minus 1, an absorption time of 5 years. In truth, A here is little more than a guesstimate. Observations of global absorption do not exist. It should therefore come as no surprise that IPCC estimates of major contributions change by as much as 100%. There's another way to determine absorption. As in the sea bath, absorption is revealed by the response to perturbation. A tracer of atmospheric CO2 is carbon-14, which comprises a small fraction of CO2 molecules. During the 1950s and 60s, nuclear bomb tests elevated C14. The nuclear source was removed in 1963 by the Nuclear Test Ban Treaty. C14 then decayed through unbalanced absorption. Just like height in the sea bath when the perturbing source was removed. The decay is almost perfectly exponential, with an absorption time just under a decade. For reference, in mauve is absorption of CO2 in climate models, the IPCC. Even after 200 years, almost 30% of CO2 present initially remains. For comparison, here's the observed absorption. Atmospheric CO2 is perturbed by fossil fuel emission. Analogous to the perturbing source in the sea bath, it introduces an anthropogenic component of CO2, Ra. Ra obeys a conservation law of the same form. The conservation law is forced by anthropogenic emission. With fossil fuel emission and alpha known, the conservation law completely determines the anthropogenic component, Ra. An upper bound follows from the slowest absorption observed, absorption time of a decade, which is apparent in the decay of carbon-14. Plotted here is fossil fuel emission, which forces the conservation law. We'll focus on years after 1960, when observation of CO2 in the free atmosphere began. By then, how much anthropogenic CO2 would have accumulated in the atmosphere? An upper bound follows by presuming that for all years before 1960, fossil fuel emission was equal to its maximum. Namely, the fossil fuel emission in 1960. Recall, the perturbation never exceeds its equilibrium level, which is the limiting level of anthropogenic CO2. In 1960, the fossil fuel perturbation must therefore be smaller than 10 ppmv. CO2 in 1960 was 320 ppmv, about 40 ppmv above 280. The anthropogenic fraction of increased CO2 must then be smaller than 24%. After 1960, anthropogenic CO2 follows by solving the conservation law. For direct comparison to the observed record, we consider changes of CO2 relative to its reference date in 1960. In red is the evolution of anthropogenic CO2. Over the last half century, it increased by about 20 ppmv. In green is the evolution of observed CO2. In 2007, the anthropogenic fraction of increased CO2 must be smaller than 28%. Remember the thermally induced component of CO2, the part coherent with temperature? It provided an upper bound on the 20th century increase of anthropogenic CO2, one that is independent of the present analysis. Applying that treatment after 1960 recovers an upper bound of 33%. What does this anthropogenic fraction mean for global temperature? Here again is the opacity of the atmosphere. It increases with increasing CO2. But because the opacity is already 100% at most of these wavelengths, the impact of additional CO2 is limited. Plotted here as a function of CO2 is the opacity collected over all wavelengths. Because opacity at most wavelengths is already saturated, the collective opacity has plateaued. Even for zero CO2, the collective opacity is already 75%. Increasing CO2 to 280 ppmv adds only 6%. Increasing it further, all the way to 400 ppmv, adds only another 0.5%. As we've seen, less than 30% of that increase is the fossil fuel perturbation. Before amplification through feedbacks, like water vapor, it introduces a temperature perturbation of less than 1/10 of a degree. Now, the projected life of fossil fuel reserves is about 100 years. At the current growth of CO2, the opacity then will have increased by another 1%. Even then, the fossil fuel perturbation represents less than 40% of the increase. It introduces an additional temperature perturbation of less than 0.3 of a degree. The cumulative fossil fuel perturbation is less than 0.5 a degree. Plotted here is the evolution of global temperature over the 20th century, at least a proxy before 1979, when satellites began actual global observations. The range of natural variability is 0.5 a degree to 1 degree. That's considerably larger than the fossil fuel perturbation just seen. Without major amplification through feedback, the fossil fuel perturbation is not even detectable. It's smaller than the noise of natural variability. Lastly, notice over this record, there is no relationship whatsoever between CO2, which increased monotonically, and temperature, which did not. And with that, we'll take a 10-minute break to enable you to grab a coffee or something cool and the speaker to wet his whistle. Everything you've seen until now is an upper bound. The fossil fuel perturbation cannot be greater. It can, however, be smaller. Turns out it is. Seeing that requires a more definitive treatment of absorption. As was apparent for the CBAT, the system's absorption is revealed by its response to perturbation. A perturbation to emission is temporarily introduced and then removed. Readjustment to the unperturbed equilibrium then reveals the time scale of absorption. In the laboratory, we would perturb the system and then monitor its response. That's what was accomplished with carbon-14 by the Nuclear Test Ban Treaty. Recall, CO2 is perturbed by changes of temperature, which modulate its emission. Perturbation in emission is then proportional to the perturbation in temperature. The conservation law is thus forced by changes of temperature. Imposing an oscillation in temperature with frequency omega will produce an oscillation in CO2 with the same frequency, but lagged behind temperature, which is continually changing. For frequency omega, much slower than absorption, alpha, the rate of change of CO2 mixing ratio, R, is negligible. The conservation law then reduces to a balance between emission and absorption. R is then directly proportional to temperature. CO2 varies in phase with temperature, with zero lag. Under these conditions, CO2 has unlimited opportunity to adjust to its instantaneous equilibrium level, which drifts with temperature. As the frequency is increased, CO2 has diminished opportunity to catch the drifting equilibrium level. CO2 then develops a lag behind temperature. As the frequency is increased, the lag is increased. At frequencies much faster than alpha, absorption then becomes negligible. The conservation law then reduces to a balance between the rate of change of CO2, that's the time derivative on the left-hand side, and thermally induced emission that forces it. CO2 then evolves like cumulative temperature the integral of temperature. At these frequencies, CO2 assumes a limiting lag of 90 degrees. CO2 oscillates in quadrature with temperature, lagging by a quarter cycle. Intermediate to these limiting forms of CO2 response is a lag of 45 degrees. It can be shown that the frequency which achieves this lag is equal to alpha, the absorption efficiency. In the lab, we would vary the frequency of the oscillation in temperature until the resulting oscillation in CO2 assumed a lag of 45 degrees. Unfortunately, this experiment is a luxury we don't have. Only one party can perform this experiment: Mother Nature. She has. Interannual disturbances like El Nino, La Nina, and volcanic eruptions perturb global temperature, which we've seen perturbs CO2 emission. Such perturbations are represented spectrally as a synthesis of frequencies, like those you've just seen. The interdependence of CO2 and temperature is then registered frequency by frequency in the coherence spectrum. Plotted here is the coherence between CO2 and temperature as a function of frequency. Where coherence extends above the shading, it's strongly significant. The relationship between CO2 and temperature is then real. In green is the respective phase of CO2. Its lag behind temperature. In blue are lags near 90 degrees, where CO2 varies in quadrature with temperature. In red are lags near 0 degrees, where CO2 varies in phase with temperature. Between those extremes is a lag of 45 degrees. The frequency at which this lag occurs corresponds to an absorption efficiency of 9 months to the -1, and absorption time of 9 months. How can this be? That's 10 times faster than what's apparent in the decay of carbon-14. The short answer is carbon-14 lies, but not intentionally. The apparent absorption time follows from exponential decay. It satisfies a conservation law with perturbing emission absent. Presumed is that when elevated C14 was taken out of the atmosphere, it stayed out. That is impossible. On a timescale of decades, C14 is conserved. When absorbed from the atmosphere, It's merely transferred to the Earth's surface. There, it's eventually oxidized, for example, through decay of vegetation. Elevated C14 is then re-emitted into the atmosphere, along with other carbon that was absorbed from the atmosphere. In the true conservation law, what actually governs C14, re-emission from the Earth's surface behaves as an auxiliary source, replacing the nuclear source before the Test Ban Treaty. It offsets absorption of C14. From the apparent and true forms of the conservation law, it can be shown that actual absorption can be only faster than that apparent in carbon-14. With an absorption time of less than a year, the anthropogenic fraction of increased CO2 isn't just smaller than 30%, it's smaller than 3%. Nature perturbs CO2 through another mechanism, one that's independent of the interannual perturbations just considered. Each year, CO2 increases and then decreases. During an interval of 8 months, from September to May, CO2 increases by 7.5 ppmv. During the subsequent interval of 4 months, CO2 then decreases by about 6 ppmv. CO2 decreases then for one reason: unbalanced absorption. Just like height in the seabed when the perturbing source was removed. Each year, CO2 goes up 5 steps of 1.5 ppmv, then down 4 steps. 5 steps up, 4 steps down. One more time. 5 steps up, 4 steps down. You have just mastered the CO2 cha-cha. Notice the residual after each cycle of the annual cha-cha is 1.6 ppmv. Ring a bell? It's identical to the trend of CO2. If we can understand one, we probably understand the other. In the seabed, removing the perturbing source reveals absorption through the time scale of decay. In one absorption time, perturbation in height decreases to 37% of the initial perturbation. In the atmosphere, the perturbation in CO2 doesn't decrease to 37% of its initial level. It decreases to only 20%. In 4 months, 80% of the perturbation has been absorbed. The absorption time could be only shorter. Notice, were the absorption time as long as 10 years, there would be no cha-cha. CO2 would then increase monotonically. 5 steps up, hesitate, another 5 steps up, and so forth. The trend then wouldn't be 1.6 ppmv per year. It would be 7.5 ppmv per year. During the last half century, the CO2 increase would have been 5 times greater. The observed evolution reveals the possible range of absorption time. What we need is annual mean absorption. During interval 2, when CO2 decreases, the mean absorption corresponds to alpha of 4.8 years to the minus 1. A lower bound on annual mean absorption follows by setting absorption during interval 1 to 0. As if during the preceding 8 months, the oceans, the land processes, and every other CO2 sink went to sleep. Alpha must then be greater than 1.6 years to the minus 1. The absorption time must be shorter than 7.5 months. Annual mean absorption can be only faster. An upper bound on absorption follows from the fastest decay. At this rate, CO2 perturbation decreases to 20% in only 3 months. Were this absorption to operate in all months, alpha would then be 6.4 years to the minus 1. Annual mean absorption can be only slower. Recall, in the sea bath, the slowest absorption produced the largest perturbation in water height. To be conservative, we'll consider the slowest absorption possible. We'll do one step better. Use alpha of 1.5 years to the minus 1, and absorption time of 8 months. Actual absorption can be only faster. The simplest treatment of anthropogenic CO2 follows from its instantaneous equilibrium level. It has the same form as the equilibrium level for total CO2, but with emission replaced by anthropogenic emission. Recall, equilibrium CO2 represents the limiting value of Ra. An upper bound on how much anthropogenic CO2 is actually present. It provides an upper bound on the anthropogenic fraction of increased CO2. In 1960, anthropogenic emission was equivalent to 1 ppmv per year. Relative to 280 ppmv, CO2 increase then was 40 ppmv. The anthropogenic fraction of this increase must be smaller than 1.6%. In 2010, anthropogenic emission increased to 3.5 ppmv per year. The CO2 increase then was 100 ppmv. The anthropogenic fraction of this increase must be smaller than 2.3%. A more detailed analysis considers the increase since 1960. when we have actual observations of atmospheric CO2. As before, we consider changes of CO2 from its reference state in 1960. Remember the sea bath? Absorption from the bath does not discriminate between native water and perturbation water. Those contributions are removed in whatever proportion they are present. Therefore, absorption does not alter the perturbation fraction of total water. It's controlled by the perturbation fraction of emission, namely, what percentage of total emission, E, comes from the perturbation in emission, E prime. The same applies to the atmosphere for CO2, which obeys a conservation law of the same form. If the perturbation in emission is now recognized as fossil fuel emission, it can be shown that its fraction of increased CO2 equals the anthropogenic fraction of cumulative emission. Namely, anthropogenic emission added over successive years divided by total emission added over the same years. That, in turn, equals the average fractional emission during a year. The average, anthropogenic to total emission. Notice, this is a direct analog of what we saw earlier under conditions of constant emission. The average anthropogenic emission follows from the record of fossil fuel emission. The average total emission follows from the observed increase of CO2. Plotted here as a function of month is net emission. It's positive during interval 1, when emission exceeds absorption and CO2 increases. It's negative during interval 2, when absorption exceeds emission and CO2 decreases. Cumulative emission during the year exceeds emission during interval 1 alone. The first 8 months, when CO2 increases. From the conservation law, that has 2 contributions. Emission must first offset absorption, which is proportional to how much CO2 is present. Otherwise, CO2 would decrease. On top of that is additional emission, equal to the observed increase of CO2, 7.5 ppmv. Total emission during the average year must exceed both contributions. It's instructive to consider the increase after just the first year, 1960. From the fossil fuel record, anthropogenic emission then introduces 0.1 ppmv. That's the perturbing emission above the reference state after 1960. For total emission, R is small enough to neglect absorption, the second term. Total emission accumulated over the year must then exceed 7.5 ppmv. In 1960, the anthropogenic fraction of increased CO2 must be smaller than 1.3%. Sound familiar? It's close to the equilibrium level. Now, there's nothing magic about 1960. Choosing 1980 as the reference date would recover much the same. Notice, this assessment is independent of alpha by design. It demonstrates that the minor impact of fossil fuel emission is fundamental. Why is revealed by comparing anthropogenic emission to total emission, each relative to that in the reference date at the beginning of 1960. What's plotted here is net emission, namely emission minus absorption. Emission, what controls the anthropogenic fraction, lies in the gray area. It exceeds 10 ppmv per year. In red is anthropogenic emission. Having trouble spotting it? Let me help you out. At only 0.1 ppmv per year, additional anthropogenic emission is eclipsed by additional total emission. This brings to light an overarching consideration. Fossil fuel emission cannot account for more of increased CO2 in the atmosphere than the CO2 which it emits into the atmosphere. All other considerations are a distant second. Now let's consider the entire period, 50 years. Average anthropogenic emission has increased to 1.2 ppmv. For total emission, absorption can no longer be neglected. It follows from the average of increased CO2 over the 50 years, about 35 ppmv. In 2010, the anthropogenic fraction of increased CO2 must be smaller than 2.8%. There's a fifth way to establish the anthropogenic fraction, and this will be brief. Rather than accumulating emission, consider the change in emission across the 50-year period. At extrema of its annual cycle, CO2 passes through equilibrium. At the minimum in 1960 and the maximum in 2010, its rate of change vanishes. There, the conservation law reduces to emission equals absorption. The change in total emission is then proportional to the change in CO2, and much the same for the anthropogenic component. Dividing the two provides an upper bound on the 50-year increase of anthropogenic CO2. The anthropogenic fraction of increased CO2 must be smaller than 2.6%. The fossil fuel perturbation is minute. Where have you seen that? Remember the sharp increase in fossil fuel emission after the turn of the century? During the decade after the turn of the century, fossil fuel emitted 3 times the CO2 that it emitted during the preceding decade. Yet the increase of CO2 in the atmosphere was virtually identical. It's now clear why. At only a couple of percent, the fossil fuel perturbation is too small to even be detectable. What about the resulting perturbation of global temperature? It's now academic. At less than 1/10 of a degree, the fossil fuel perturbation is buried in the noise of natural variability. The fossil fuel perturbation is presently not detectable. It will not be detectable, ever. Here's how we can be certain. The fossil fuel perturbation is too small to be distinguished from natural changes. You can't distinguish it, nor can feedback mechanisms. Consequently, whatever influence they exert on the anthropogenic component, they must simultaneously exert on the natural component. Ergo, if the fossil fuel perturbation is buried in the noise before feedback, it will remain buried in the noise. The size of the fossil fuel perturbation evokes a slogan which became the anthem of the climate change movement. In retrospect, never has so much been claimed on the premise of so little. As you know, the climate change movement culminated in the recent international agreement in Paris. Its projected cost, just under $360 trillion. That's $20,000 for every man, woman, and child on Earth. And to be rhetorical, many of those humans won't even earn $20,000. The harsh reality is this cost is borne disproportionately by the disadvantaged in more ways than one. Last winter, in Europe alone, 40,000 poor and elderly perished through hypothermia because under spiraling costs to feed green ideology, they could no longer afford to heat their homes. My God, what an indictment of this era. Even Neolithic humans could heat their homes. In light of its cost to the public, what will the Paris Agreement achieve? The prospective benefit can now be evaluated. It's revealed by turning back the clock. In green is the observed evolution of CO2. during the last half century. Had fossil fuel emission been eliminated entirely, CO2 would then have evolved in blue. It's appropriate to close with a retrospective, to place the treatment of this subject in the historical context of how science has advanced. At the core of the debate surrounding climate is a struggle between scientific rigor, which is accountable to nature, versus pseudoscience, which is not. Distinguishing the two isn't brain surgery. One sphere excludes evidence by declaring its conclusions are beyond question. The science is settled. Its advocates know this because they took a vote. The other sphere relies on reason, continually testing its understanding against new evidence. Accordingly, it holds that science is never settled. The struggle between these opposing interests has happened before. One of the benefits of modern civilization is medical science. If you become ill, you have every expectation of competent treatment by a practitioner who operates in the reality of human physiology. It wasn't always so. Early medical treatment was a cross between superstition and pseudoscience. If illness didn't kill you, the cure likely would. The tools of the trade would make a trip to the dentist look inviting. And of course, the procedures were conducted before the advent of anesthesia. They relied upon the theory of the Roman physician Claudius Galenus, or simply Galen. Galen's theory postulated that well-being was controlled by 4 bodily fluids, or humors, one of which was blood. In Galen's theory, blood motion was one way. Blood was continually produced by the liver, then transmitted by the heart to the rest of the body, where it was consumed. An imbalance of the humors produced illness. From this belief sprang the practice of bloodletting. Removing blood would rebalance the humors, supported by the belief that blood was continually replenished by the liver. So influential was Galen's theory that it guided medical treatment for nearly 2,000 years. Enter William Harvey. Harvey had conducted extensive dissections which revealed the mechanics of blood. On Galen's theory, Harvey was suspicious, dare I say, skeptical. In light of his observations, he was increasingly confronted with the obvious. To demonstrate it, Harvey performed a fundamental calculation. From dissections, he knew the volume of the heart. He knew also the pumping cadence, the number of beats per minute. Combining the two determined the volume of blood, which under Galen's theory would have to be produced each day. Harvey knew he'd be bucking the establishment, so he intentionally lowballed the calculation. He chose values so low that the true blood volume could be only greater. Harvey's calculations showed that Gallen's theory would require a daily production of blood exceeding 1/4 of a ton, more than a 55-gallon drum. To produce this blood, that's how much a human would have to consume in one day. Gallen's theory went the way of the dodo. As we now take for granted, blood is not consumed, but recirculated. Despite Harvey's clear invalidation, Gallen's theory continued to be practiced for nearly 200 years. Among its victims, George Washington. To treat a throat infection, Washington's physicians drained his blood, 80% of it. 72 hours later, Washington was dead. After being invalidated, why did Gallen's theory continue to be practiced? The answer is simple. An enterprise will never voluntarily relinquish that upon which it thrives. George Washington was triumphant over the might of the British Empire. He was destroyed by the incompetence of pseudoscience. Harvey's findings vitiated the foundation of medical practice, a belief that had prevailed for nearly 2,000 years. Harvey described the reaction to his findings as an uproar. To his critics, Harvey responded as follows: I profess to learn and teach anatomy not from the tenets of philosophers, but from the fabric of nature. For hundreds of years, that has been the objective of science: to understand nature. Contrasting fundamentally is the new environmental science. Climate science moderna, with the answer predetermined by government bureaucracy under the aegis of the UN. Its objective has become an exercise in social engineering. To predict and control the undetectable. Had resources been invested to better understand this complex system, the fallacy might have been discovered sooner.